The search for life beyond Earth demands a comprehensive understanding of the precise conditions that enable biological systems to emerge and flourish across the cosmos. At the heart of this quest lies the concept of habitable zones, regions around stars where planetary surfaces can potentially support liquid water, widely considered essential for life as we know it. The Circumstellar habitable zone, often called the Goldilocks zone, represents orbits where conditions are neither too extreme nor too mild, but just right for maintaining liquid water given sufficient atmospheric pressure. Current scientific estimates suggest our galaxy may harbor approximately 40 billion Earth-sized planets, orbiting within habitable zones of Sun-like stars and red dwarfs, with roughly 11 billion potentially orbiting stars similar to our Sun. Beyond the traditional focus on stellar energy and liquid surface water, scientists now recognize alternative habitability scenarios, including deep biospheres sustained by tidal heating or radioactive decay, potentially extending the range of habitable environments to surprising locations such as rogue planets or moons with subsurface oceans. This comprehensive exploration examines the multifaceted conditions required for life to thrive from an astronomical perspective, incorporating established knowledge while acknowledging evolving understanding of extreme environments and their potential to harbor unexpectedly resilient forms of life. Liquid water stands as the most fundamental prerequisite for life as we understand it, functioning as what astronomers and astrobiologists consider the universal solvent necessary for complex biochemical processes. Water provides the medium in which organic molecules can dissolve, interact, and participate in the chemical reactions essential for metabolism and reproduction, processes fundamental to all known living systems. The unique molecular properties of water, including its polarity, hydrogen bonding capabilities, and remarkable thermal properties, create an ideal environment for the complex chemistry of life. These properties allow water to dissolve a vast array of compounds while maintaining stable temperatures, which shields organisms from rapid environmental fluctuations that could otherwise disrupt delicate biochemical processes. The search for extraterrestrial life thus prioritizes environments where liquid water can persist, as evidenced by the central role water plays in defining habitable zones around stars throughout our galaxy and beyond. This water-centric approach to habitability has guided astronomical research for decades. Though our understanding continues to evolve as we discover increasingly diverse environments where water might exist in liquid form, the existence of liquid water depends critically on both temperature and pressure conditions, creating a specific parameter space within which life might thrive across different astronomical environments. On Earth, water remains liquid between 0 degrees C and 100 degrees C at standard atmospheric pressure, but this range can vary significantly under different pressure conditions, potentially expanding habitable niches. Higher atmospheric pressures, such as those that might exist on super-Earth exoplanets with stronger gravity, can maintain liquid water at temperatures exceeding Earth's boiling point, potentially extending habitable zones outward from parent stars. Conversely, extremely low pressures, like those found on Mars, restrict liquid water stability to narrow temperature ranges and specific locations, such as the lowest elevations of Hellas Basin, where pressures can reach 1,115 Pa, allowing temperatures to rise above 0 Celsius for limited periods during the Martian year. The interplay between pressure and temperature creates complex habitability patterns across different worlds, with estimates for the solar system's habitable zone ranging dramatically from conservative calculations to more optimistic assessments. These variations highlight the challenge of defining precise boundaries for potential life-supporting environments, particularly as we discover worlds with atmospheric compositions and pressures radically different from Earth's. While water remains the focus of traditional habitability assessments, astrobiologists have proposed expanding our search to include environments where alternative solvents could potentially support exotic forms of life based on fundamentally different biochemistry. Some researchers suggest that solvents such as dihydrogen, sulfuric acid, dinitrogen, formamide, and methane might serve as bases for biochemical processes under conditions where water cannot exist in liquid form. These alternative biochemistries would necessarily employ different chemical pathways and molecular structures than terrestrial life, potentially utilizing silicon instead of carbon or ammonia rather than water as the fundamental medium for biological processes. The physical properties of these alternative solvents, including their freezing and boiling points, viscosity, and solvent capabilities, would create unique constraints and opportunities for any life that might employ them. Such considerations have led to proposals for circumplanetary habitable zones and other expanded habitability concepts that encompass environments previously considered hostile to life. These theoretical frameworks acknowledge that our understanding of life's requirements may be limited by our Earth-centric perspective, particularly since Earth's biosphere represents just one evolutionary pathway among countless possibilities that might exist throughout the cosmos. The concept of regions around stars where life might thrive has evolved significantly since its earliest formulations, reflecting centuries of advancing scientific understanding. The earliest recognizable reference to what we now call the habitable zone appeared in Newton's Principia, where he estimated the range of distances from the Sun that might allow for the existence of liquid water. This foundational idea gained further refinement in 1802, when philosopher Louis-Claude de Saint-Martin speculated about Earth occupying a necessary rank and distance from the Sun to support vegetation, implying that other planets might be too close or too distant for similar processes. The term habitable zone itself first appeared in Edward Maunder's 1913 book, Are the Planets Inhabited?, marking an important conceptual milestone. The mid-20th century brought significant advances with Hubertus Strughold's 1953 treatise, introducing the term ecosphere, and Harlow Shapley's liquid water belt description from the same year, both emphasizing liquid water's crucial importance to life. These early frameworks laid essential groundwork for understanding planetary habitability, while acknowledging the centrality of water in supporting biological processes. The contemporary understanding of habitable zones emerged through increasingly sophisticated models developed during the late 20th century, incorporating atmospheric science, planetary geology, and astronomy. Stephen H. Dole's 1964 book, Habitable Planets for Man, represented a significant advancement, discussing the circumstellar habitable zone while estimating approximately 600 million habitable planets might exist in the Milky Way, a number now considered quite conservative. Around this same period, Isaac Asimov helped popularize the concept through science fiction explorations of space colonization, bringing these scientific ideas to broader public attention. The term Goldilocks zone emerged in the 1970s as an accessible metaphor for the region around a star with temperatures just right for liquid water, drawing on the children's fairy tales theme of finding the perfect middle ground between extremes. A pivotal contribution came in 1993, when astronomer James Casting introduced the more precise term circumstellar habitable zone and presented the first detailed model for exoplanet habitable zones. Casting's work forms the foundation of the most widely used definition today, centering on the range of orbits where planetary surfaces can maintain liquid water given appropriate atmospheric conditions. The evolving understanding of extreme environments has led to the development of dual frameworks for habitable zones. Conservative estimates focused on Earth-like conditions and extended calculations incorporating a broader range of potential life-supporting scenarios. Conservative habitable zone models typically focus on lower mass planets like Earth with thinner atmospheres and modest greenhouse effects, creating relatively narrow bands around stars where liquid water could exist. In contrast, extended habitable zones account for super-Earth planets with stronger gravity that can maintain thicker atmospheres and more robust magnetic fields, potentially allowing surface water at greater distances from their stars. These expanded zones recognize that planets with enhanced greenhouse effects, similar to Venus but less extreme, might maintain habitable surface temperatures despite receiving less stellar radiation than Earth. The difference between these estimates can be substantial. Koparapu's 2013 calculations placed conservative solar system habitable zone limits at 0.991.67 AU, while Pierre Humbert and Gaidos suggested terrestrial planets with significant primordial hydrogen atmospheres might remain habitable as far as 10 AU from the Sun. These divergent estimations reflect fundamental uncertainties about how different atmospheric compositions and planetary characteristics might combine to create habitable conditions across diverse astronomical settings. The determination of habitable zone boundaries incorporates multiple astronomical and planetary factors, creating a complex multidimensional parameter space that researchers continue to refine through increasingly sophisticated modeling approaches. 3 primary factors determine whether a body falls within its star's habitable zone: the radius of the planet's orbit, the mass of the planetary body itself, and the radiative flux received from the host star. Early models by researchers like Dole used relatively simple parameters, employing optically thin atmospheres and fixed albedos to calculate habitable boundaries, placing Venus's aphelion just inside the inner edge. Subsequent refinements introduced more complex considerations. Budico's work utilized ice albedo feedback models to determine points at which Earth would experience global glaciation, while Rasool and DeBerg's research analyzed Venus's atmosphere to establish minimum distances at which Earth could have formed stable oceans. Modern computational approaches incorporate sophisticated climate modeling, with HART simulations of Earth's atmospheric evolution, and Casting's landmark research assuming that carbon dioxide and water vapor function as key greenhouse gases, similar to Earth's atmosphere. Contemporary approaches continue this evolution, with 3-dimensional models producing more precise inner edge calculations and correlating habitable conditions with specific water mixing ratios, surface temperatures, and climate sensitivity parameters. Stars of different spectral classes create vastly different environments for potential life-bearing planets, with their mass, temperature, and lifetime determining fundamental habitability parameters. Massive O and B-type stars burn intensely, but briefly, often for less than 100 million years, generally considered insufficient time for complex life to evolve based on Earth's developmental timeline. These massive stars also produce immense amounts of harmful ultraviolet radiation that would likely strip away atmospheres and damage biological molecules on nearby planets. In contrast, smaller K and M-type red dwarf stars burn their nuclear fuel much more efficiently, potentially remaining stable for trillions of years, giving any life that might develop around them substantial time to evolve and adapt. However, these smaller stars present their own challenges for habitability. Planets must orbit much closer to receive sufficient warmth, placing them within range of stellar flares and potentially locking them in synchronous rotation, where one hemisphere perpetually faces their star. According to Koparapu's habitable zone calculations, a star with just 0.25 times the Sun's luminosity would have its habitable zone centered at only 0.67 AU, significantly closer than Earth's 1.34 AU distance from the Sun. This proximity creates complex trade-offs, as planets receiving appropriate levels of warmth from smaller stars must contend with increased radiation and gravitational effects that could compromise their habitability through various mechanisms. A star's stability over long time periods plays a crucial role in determining whether life can emerge and thrive on its orbiting planets, with various types of variability, potentially disrupting the delicate conditions required for biological evolution. Main sequence stars like our Sun generally provide relatively stable energy output over billions of years, with only moderate fluctuations in luminosity that allow planetary climates to maintain equilibrium conditions suitable for biological processes. This stability represents a fundamental prerequisite for the development of complex life, which requires consistent environmental conditions to evolve increasingly sophisticated adaptations over geological timescales. As stars age, however, they undergo significant evolutionary changes. Our Sun, for instance, has increased its luminosity by approximately 30% since Earth's formation 4.5 billion years ago, gradually shifting the habitable zone outward. This stellar evolution creates moving targets for habitability, potentially rendering once suitable planets too hot, while bringing previously frozen worlds into temperature ranges compatible with liquid water. The habitable zones of smaller M-dwarf stars move much less dramatically over time due to their slower evolution, potentially providing more stable long-term environments despite other challenges like increased flare activity and radiation. These stellar evolutionary pathways create complex temporal patterns of habitability that significantly influence where and when life might develop across different regions of our galaxy. The radiation environment created by a star represents both an essential energy source for life and a potential hazard, requiring planetary systems to balance these competing factors through various protective mechanisms. Stars produce a spectrum of electromagnetic radiation, from life-enabling visible light that powers photosynthesis to potentially harmful ultraviolet and X-ray emissions that can damage biological molecules and strip away planetary atmospheres. Young stars and smaller M-dwarfs typically emit proportionally more high-energy radiation, creating challenging conditions for potential life on their planets. Effective protection from this radiation requires several planetary features working in concert: a sufficiently thick atmosphere to absorb harmful wavelengths, a magnetic field to deflect charged particles, and possibly an ozone layer or similar protective atmospheric component to screen out ultraviolet radiation. Earth exemplifies this balanced protection system, with its magnetic field shielding against solar wind particles, while atmospheric gases filter harmful wavelengths, allowing beneficial radiation to reach the surface, where it can support biological processes. The requirement for these protective features narrows the range of truly habitable worlds, as planets must not only orbit within appropriate temperature zones, but must also maintain complex systems that shield their surfaces from harmful stellar emissions. This multifaceted radiation balance represents one of the most significant challenges for potential life around stars different from our Sun, particularly the numerous red dwarf stars that comprise the majority of stellar objects in our galaxy. Binary and multiple star systems, which actually constitute the majority of stellar systems in our galaxy, present unique and complex challenges for planetary habitability, significantly affecting where stable life-supporting environments might exist. American astrophysicist Sushu Huang argued as early as 1960 that circumstellar habitable zones, and by extension extraterrestrial life, would be uncommon in multiple star systems due to gravitational instabilities. These gravitational complexities can create highly variable orbits, where planets experience dramatic temperature fluctuations as they move closer to and further from their host stars, potentially rendering their surfaces inhospitable, despite technically residing within habitable zones. Multiple star systems can support stable planetary orbits in two primary configurations: circumbinary orbits, where planets circle both stars as if they were a single mass, and wide binary arrangements, where planets orbit just one star at a sufficient distance from the companion star to avoid gravitational disruption. The habitability implications differ significantly between these configurations, with circumbinary planets potentially experiencing complex day-night cycles and seasonal patterns unlike anything observed in our solar system. Stable orbits represent a fundamental prerequisite for habitability in these systems, as planets must maintain relatively consistent distances from their host stars to preserve temperature ranges compatible with liquid water and biological processes. Despite these challenges, the sheer abundance of multiple star systems suggests they cannot be dismissed in the search for life, though they likely present more constrained habitable regions than single stars like our Sun. A planet's mass exerts fundamental influence over multiple habitability factors, creating a specific range within which complex life is most likely to emerge and flourish. Sufficiently massive planets, generally at least 0.3 Earth masses according to some models, can maintain internal heat through radioactive decay and primordial thermal energy for billions of years, driving the geological activity necessary for long-term climate regulation through mineral weathering and volcanic outgassing. This internal heat also helps generate and maintain planetary magnetic fields, which shield surface environments from harmful stellar radiation. At the upper mass limits, planets several times more massive than Earth, super-Earths, can maintain thicker atmospheres due to their stronger gravitational pulls, potentially extending habitable zones outward, as these atmospheres create stronger greenhouse effects. However, extremely massive planets present challenges for potential life. Those exceeding approximately 10 Earth masses typically accrete substantial hydrogen-helium envelopes during formation, becoming mini-Neptune-type worlds with extreme atmospheric pressures unsuitable for Earth-like biochemistry. The relationship between planetary mass and surface gravity also influences atmospheric composition and biological constraints, as stronger gravity requires organisms to develop more robust support structures, while also affecting atmospheric density gradients and circulation patterns. These interconnected effects of planetary mass create a complex parameter space where multiple factors must align to create truly life-supporting environments across different stellar systems. A planet's atmosphere serves multiple critical functions for habitability, requiring specific compositions and pressures maintained over geological timescales to support complex life. The primary gases in an atmosphere determine fundamental climate properties through greenhouse warming, with carbon dioxide and water vapor functioning as key temperature regulators in Earth's system and likely in other habitable environments. Atmospheric pressure proves equally important, as pressures below approximately 15 millibars appear insufficient to maintain stable surface liquids, according to Vladilo's 2013 research. Higher atmospheric pressures can significantly expand habitable zones, both inward towards stars by creating stronger cloud albedo effects that reflect excess radiation, and outward through enhanced greenhouse warming that traps more heat. The atmosphere's redox state, oxidizing versus reducing, determines which chemical reactions predominate on a planet's surface, with oxygen-rich environments enabling energy-intensive metabolic pathways that support complex multicellular life. A planet's ability to retain its atmosphere against solar wind erosion and thermal escape depends on both its mass and magnetic field strength, with smaller planets like Mars losing substantial atmospheres over time while Earth has maintained relatively stable conditions. The complex interplay between atmospheric composition, pressure, and retention creates specific requirements for truly habitable worlds, explaining why, even within our solar system, planets like Venus and Mars, both technically within various habitable zone estimates, fail to support surface life due to runaway greenhouse effects and atmospheric loss, respectively.